Welcome back, everyone. So in this video, what we're going to do is we're going to talk about Snell's law. Okay, Snell's law. Now, what does Snell's law tell you? Well, if you recall from the previous video, when we talked about the index of refraction, basically what happens is as light goes from one medium to another, it will change speeds depending on what the different indices of refraction are. So, in other words, a material with a lower index of refraction, it will travel faster. In a higher index of refraction, it will travel slower. Now, changing speeds is not the only thing that will happen as it goes from one medium to another, right? Just like the definition of refraction is the light will bend, right? Snell's law tells you how much it will bend. Okay, so Snell's law is another way to say the law of refraction. So it looks like this. Okay, just write it down real quick, and then I'll show you. Okay, here it is. N1 sine theta 1 equals N2 sine theta 2. So in other words, as light in the first medium, whatever that index of refraction is, enters the second medium at some angle, okay, it will bend to a new angle based on the new index of refraction. All right, so what we're going to do is take a couple minutes and take a look at how that behaves as it goes from one medium to another in all these different kinds of scenarios. All right, and then in another video, we'll do a practice problem or two with this equation. All right, so let's start with the first scenario. Okay. Okay. So our first scenario will go from air into water. Okay, air has an index of refraction of 1. Water has an index of refraction of 1.33. Okay, so we're going from a lower index of refraction to a higher index of refraction. Okay, so the light will come in at some angle. Just like always, we measure to the normal. Okay, so we're measuring, here's our normal, this dashed line that's perpendicular to the surface. We measure it to the normal. Now, as light goes from air, a lower index, to water, a higher index, it will slow down, right? Because water will have a greater index of refraction, which means it slows down. But it will also bend toward the normal. Okay, it will bend toward the normal. Now, I made it a bit of an exaggeration for just our purposes, but you can figure that out in the calculation. Okay, so as it goes from a lower index to a higher index, it will slow down and bend toward the normal. Alrighty, so that's one scenario. Let's go with another scenario. Okay, let's say this time the light is going from zircon, which is some mineral, into water. Okay, the index of refraction for zircon is 1.92, and water again is 1.33, and it's going to go from that zircon into the water. So it's going from a higher index of refraction to a lower index of refraction. Right? So again, we measure to the normal. Here's our incident angle. And as it goes from zircon into water, it will speed up since water has a lower index of refraction, and it will also bend away from the normal. Okay, so it'll look like this. Again, I didn't exactly measure it. It's exaggerated just for effect. Okay, so here we go. Goes from a higher index to a lower index, bends away from the normal. That angle gets a little bit bigger. Okay, awesome. Another scenario. What happens if you go from, say, corn oil to glycerol? Okay, my normal. Corn oil has an index of refraction of 1.46. Glycerol has an index of refraction of 1.46. In other words, they have the same index of refraction. All right, so what happens here? Well, as the light enters, it's going to pass on through as if nothing happened. It will not change speeds, right? N equals c over v, so if the n is the same, the v, the speed of light, is the same. And if you were to plug these values into your Snell's law equation, you'd find that the angle, as measured to the normal, will be the same. So it just passes straight through. There's no change in speed. There's no difference, okay? They have the same index of refraction. There's not going to be any change, right? It's why you don't notice any refraction as light just passes through air, okay? It's all the same index of refraction, so there is no refractive effects. It has to change the index of refraction for there to be that effect, which is why you see it in a pool or in a lake or something like that, or why your glasses are used to help you see better, okay? And one final scenario we're going to get to, let's just say N2, N1, and N2, okay? Okay. The reason I made those general is because this is true in all the cases, right? So what happens if you're changing medium? So these are different indices of refraction. They can be the same. It's all going to be the same. But for now, let's just say they're different. What happens if the light enters the new medium along the normal? In other words, perpendicular to the surface. Okay? Well, in that case, the light will not bend. It will just pass on through. But unlike the other scenario where it didn't change speeds, this will still change speeds. So if N1 is greater than N2, it will speed up. If N1 is less than N2, it will slow down. Right? It'll still follow that part of the rules. It's just as it enters along the normal, it will just keep on going. Okay? And you can verify this with Snell's law. But again, that's going to be in the other video about using Snell's law. So those are the basic principles of Snell's law. You saw the equation. You saw the scenarios that kind of arise from those from that equation. And the next video you see will be on calculating different things. I'll do one practice problem where you're calculating a new angle and one where you're calculating a new index of refraction, or index of refraction. Okay? I'll see you then.